Okay, so any questions? Everything makes sense? Yeah? All right. Well, good. So we are in chapter 5. We just did first two sections, and the homework and the quiz is due tonight on 5.1 and 5.2. So let's just quickly recap the exponential function. So again, the definition of an exponential function is something like this, where a is positive and not equal to 1. That's what we agreed on, because the negative base would make it a nightmare of a domain type of thing, because remember, the fractional exponents mean radicals, so you might end up taking square roots of negative numbers a lot, so that's going to be hard. And if a equals 1, then it's just a very, very boring function. So that's what we agreed on. And the graph in general, the graph of an exponential function looks like this, goes through 0, 1. And that's if a is greater than 1, or going down if a is between 0 and 1. So we have those two cases, right? No? Yeah? Now, what is the domain of an exponential function? All real numbers. What is the range of an exponential function? Right, strictly positive. So what is the y-intercept? What? Yeah, 0, 1. And it also has a horizontal asymptote, which is the x-axis. Right, so x-axis. But we also notice, just by looking at these graphs, we can say that these functions are one-to-one, right? Just by looking at the shape of the graph of an exponential function, you see it passes the horizontal line test, therefore it's a one-to-one function. So exponential functions are one-to-one. How's that? Good? Okay, well, since exponential functions are one-to-one, we can make a certain conclusion about them. If a function is one-to-one, that it possesses what? What do one-to-one functions have? Anyone? Mikey, what do one-to-one functions have? Oh, you just gave me a definition. That's fine, but if a function is one-to-one, I mean, why do we even care? Well, what does that give us? An inverse, right? Since function is one-to-one, we know it has an inverse. So let's start talking about the inverse of exponential functions. So that's the section 5.3. Well, I know everything there is to know about this inverse. Okay? So let's talk about the inverse Inverse of an exponential function. Can you tell me the domain of the inverse? What is the relationship? Right, the range of the function becomes the domain of the inverse function, right? So just strictly positive. Right, so the domain, I'm going to switch colors on this one. So the domain of the inverse function would be strictly positive, right? What about the range of the inverse function? All real numbers. So now, and I can sketch the graph of that inverse, right? Let's just focus on the case where a is greater than 1. So this right here is a graph of a to the power x, right? And it passes through a point 0, 1 and has a y-intercept at 1. So therefore, what can you say about the intercept of an inverse function? Will it have a y-intercept or an x-intercept? X-intercept. Remember how we flip the order of x and y? So the inverse function will have this point, 1, 0. So it has an x-intercept. And I can sketch the graph of that function because we remember that in order to sketch a graph, of an inverse, I have to reflect the graph of a function across the line y equals x. And here's the line y equals x. So if I do that, so here's my y-axis. Now remember that exponential function had a horizontal asymptote at the x-axis. So if you start flipping everything, you're going to end up with a vertical asymptote at the y-axis. So actually you're going to have a vertical asymptote at the y-axis, or x equals 0. Well, then just visually flip the blue line. You're going to end up with something like that, right? You have an asymptotic behavior as the graph approaches the y-axis. So it looks something like that. So we know everything there is to know about the inverse function except for the name, and that's really minor. We're just going to make up a name. Okay, that's really what happened. Just gave that function a name, and we decided to call that a logarithmic function. So that's what a logarithmic function is. That's the graph of a logarithmic function, and it's just an inverse of an exponential function. Okay? Yeah, and I'll define it in a second. So that would be the graph of a logarithmic function, but that's the inverse of exponential function. Called logarithmic function. So this is the notation log for a logarithm. Then we'll put the little a like that. So that represents the base, and then the variable x. So this reads as log base a of x. Okay? Now the properties stay the same. The domain of a logarithmic function is strictly positive. The range would be all real numbers. Has an x-intercept at 1, has an asymptote at the y-axis. So that would be the graph. But it doesn't go to the left, right? So we only use positive x values to come up with that graph, right? But it spans negative and positive, so the range is all real numbers. Okay? So this is how you pronounce it, log base a of x. So a would be the base. So just the definition. So let me ask you this question. If I define a function f of x equals 2 to the power x, so that's an exponential function, right? And what does this function do? If I throw in a number for x, what is that function going to do to that number? I mean, what will the output of that function be? No, I'll give you that exponent. It will tell you what 2 raised to that exponent would be. Right? No, that's not what you said. You said the opposite. Well, that's the big difference, right? So if given a value for x, right, f of 3, we will find out what is 2 raised to that power would be. That's 8, right? If I ask you what is f of negative 4, it is 2 to negative 4, so it's 1/16, right? So exponential function, given the exponent, it tells you what you get if you raise base to that exponent, right? You would know that. So the inverse function, then, should do the opposite. If I look at the inverse function, that would be log base 2 of x, right? So again, with the exponential function, you give a power, you get an output, right? So with the inverse function, it should be the opposite. You fit in the output and you get the power back. So if I ask you, what is f of 8? So this is log base 2 of 8. What really I'm asking is to what power I need to raise 2 to get 8. So log base 2 of 8 really is asking you to what power we need to raise 2 to get 8. So it's the opposite of what an exponential function is doing. By the way, do you know the answer to that? 3. Okay? So the logarithmic functions, the output of a logarithmic function is an exponent. Okay? You give a value which you want to get, and the logarithm will tell you to what power you need to raise the base to get that value. Is that okay? So again, so if you have something like this, log base a of b, that means to what power to raise a in order to get Is that okay? So if I throw another way to define it, if you log base a of x equals y, this is equivalent to saying that a raised to the power y equals x. So these two are equivalent. So again, the logarithm gives you the power such that if you raise a to that power, you're going to get the input. So let's just do a few examples. We'll get that pretty fast. So let's say if I have log base 3 of 9. So the question is, to what power do we need to raise 3 to get 9? 2, right? So that equals 2, because this is equivalent to saying 3 raised to the power 2, you get 9 back. So that's what that definition above is. Okay? Well, of course not. Right? If I just change that, if I say log base 3 of 8, then we're done. Right? We cannot. You calculated, not really. Well, we'll get to that point. But you're right. I mean, it's not. I mean, I can give you a bunch of examples that are obvious like that. But then if I give you something like log base 3 of 8, you know it's probably less than 2, but bigger than 1. Bigger than that. So, I mean, we'll get that by the end of today. I promise you that. But for now, let's just do the ones that we can do in our heads, right? So let's say if I give you log, I don't know, base 5 of 1/5. So again, the question is, to what power I need to raise 5 to get 1/5? -1, good. Because 5 to the power -1 equals 1/5. So the thing on the left, we're going to call it the logarithmic form. The expression on the right is the exponential form. And we should be able freely to interchange between one and the other. What do you mean by? No, you don't. Yeah. I know you came in a little late. This is what you get if you graph a logarithm, the green line. Okay. But yeah, for now your calculator is very limited. If I ask you to use a calculator to do log base 5 of 1/5, you need to learn something else before you do that. Your calculator lacks that button. But anyways, but you understand what kind of we're doing here? If I ask you what is log base 10 of 100, you would say 2, because 10 squared equals 100. How about, no, you don't. But I'm just explaining why that's the case. Usually if they ask you just to evaluate, you just give the answer. Sometimes they'll ask you express in the exponential form to go back and forth between two. But what if I ask you log base 17 of 17? 1, right. Because to what power I need to raise 17 to get 17? Well, that'll be 1. Agree with that? Here's a silly question. How about log base 17 of 17 to the power 5? We don't know that yet. But all we know is the definition. It's almost a trick question. It's 5, right? To what power you need to raise 17 to get 17 raised to the power 5? 5. All right. Good. It's almost a trick question because 17 to the power 5 equals 17 to the power 5. Agree with that? Okay. How about log base 17 of 1? 0. To what power you need to raise 17 to get 1? And the answer is 0. 17 to the power 0 equals 1. Okay? Okay, how about this one? What if I take 17 and raise it to the power of log base 17 of 5? Because again, log is just a number, right? Keep that in mind. Log base 17 of 5 is just some number. So I just decided to raise 17 to that number. What do you think that equals? I know some of you know that clearly. You've seen some of the properties. 5. You just guessed that. Now let's try to reason through this one. well, I don't think I followed your explanation, but okay. Well, let's just focus on log base 17 of 5. What is that? Log base 17 of 5 is some magic number such that if I raise 17 to that number, I'll get 5, right? Well, here I'm raising 17 to that number. 17 raised to the number that turns 17 into 5 by the means of raising 17 to that power. So, well, here we go. Well, it matters. I mean, if I change the base, if I make this instead of 17, 15, it won't work. Okay? But the idea again, because look, log base 17 of 5 equals x implies 17 to the power x equals 5. That's the exponential form. 17 raised to that power equals that number. Well, here I'm raising 17 to that number, right? I'm raising 17 to the power x. So that one is confusing. Okay?
How is that one different than the one in
That one? Well, it's different order of operation, right? Here I'm doing the power and then taking the log. Here I'm taking the log inside the power. So it's really kind of different order of, you see, I'm doing exponential logarithmic functions in different order. Okay? But just from this little list, we can get some properties of logarithmic functions. So again, let a be positive, not equal to 1. The properties of the base stay the same between exponential logarithmic functions. Base has to be strictly positive. Base cannot equal to 1. Then we have 4 properties. If I take log base a of a, we'll get 1. As we saw, log base 17 of 17 was 1. So if the base matches the inside, the answer is always 1. Because to what power do I need to raise a to get a? Well, the answer is 1. Right? Right, that's the first property. The second property, yeah, well, there's nothing I can do about that. I mean, I would move if I were you. But other than that, well, the rest of you should be okay. But it's just, I don't know. Log base a of 1. Again, we just saw an example like that. What is that equal to? 0, right? To what power I need to raise a to get 1? So any number to the power 0 equals 1. Any number other than 0, and since base is strictly positive, we're safe there. Right? Because 0 to the power 0, undefined. Did we have a problem with our calculator in this class? With 0 to the power 0? Yeah, but, yeah. Anyways. If we have log base a of a, log base a of a to the x, what is that? X. To what power I need to raise a to get a raised to the power x, that's x. And the fourth property is a raised to the power log base a of x also equals x. Right? Now, again, the property 3, we were able to see that just based on the definition. That should be pretty straightforward. But property 4, that was one a bit confusing. Right? That one is a lot harder to see, and I agree with that. It's harder to see property 4. But let me show you something. If I consider these two functions, f of x equals a to the x, and g of x equals log base a of x. So I have these two functions. And what if I decide to compute a composition f of g of x. So how would that work? What is the composition? How would you write it? No, that's f of g. Yeah, this is that composition symbol. Remember that? You might have missed that day, but that's the composition, right? Well, yeah. Yeah, it will be a raised to whatever we're raising, whatever we're putting inside. So it's a to the power log base a of x, right? So it does look like a property 4 when I actually do the composition, right? But since, what do we know about these two functions, exponential function, logarithmic function? What is the relationship? The inverses. So every time you take compositional function, the inverse, you automatically get x. Just by the definition of the inverse functions, right? Every time we compose inverses, the x falls out. So that's another way to see why a raised to the power log of the same base just gives you the input back. You just have to know the property. But I'm just trying to justify that, right? Because we are, well, in college, right? But are you buying that? I mean, you've bought it before, the previous explanation, but this is another way to see that. And if I reverse the order, if I do g of f of x, so I'm putting f inside of g, so that would be log base a of a to the x. So that's our third property. So also equals x, whether just the way we understand logarithms, or just because of the fact that we're taking a composition of a function and its inverse. So it should give me x back twice. So this is why these last two properties are called inverse properties, because they're based on the fact that these are compositions of inverse functions, so inverse properties. How is that? Interesting. Well, I'm glad you find that interesting. But anyway, so these are our 4.
There's no more properties, that's all.
You're going to have 3 very major laws, but that would be basically it. Yeah, because again, the last 2, they correspond to compositions of functions and inverses. So just by the definition, we should get x in both cases. No, calculators are very useful for this, but for now they are well, your calculators are very limited. Well, I don't. Well, see, if you can, then sure, go ahead. But your calculators, any calculator, no matter how fancy it is, when you open it up, it will only have 2 logarithmic buttons. Okay, if you have your graphing calculator for $150, so you have just a basic scientific calculator for $1, they all have just 2 logarithmic buttons. Well, one of them is right here, the log, right? Gave me invalid input because I just computed log of 0. 0 is not in the domain, so that's okay. Okay, so there are only 2 buttons. Here's one, log. Here's another one, ln, and I'll talk about those in a minute. So you only have 2 buttons, log ln, and that's really enough to compute every logarithm there is. What's with the, okay. But, so the log. I'm going to talk about this one in a minute. So we'll call it a common log, which basically means log base 10. Just like with the square root, you don't write a little 2 in the radical sign. With logarithms, if it's base 10, we don't even write base 10. So every time you see an expression like log of x, that really implies log base 10 of x. We don't write that base 10. Okay, so every time when you see a log without a base, base 10 is implied. Okay? So again, I can ask you what is log of 10, you'll say 1. Because the base 10 is implied there. So I'm asking for a power unit raised 10 to get 10, so the answer is 1, right? And if I ask you what is log of 1, you'll still say 0, because 10 to the power 0 equals 1. I can ask you what is log of 0.01. You'll be able to answer that without your calculator. -2. Right, -2. Why? Well, because 10 to the negative second power is 0.1. But go ahead. This is exactly what I wanted to ask. How do you say this number? 1/100th. So if you pay attention to the language, that's what it is. 1/100th, right? So now you see, all right, I need to change 10 to 100, so that's the squaring, and then flip it, so that's the negative. So that's how you get the negative second power. Right, because the square will turn 10 into 100, and the negative will flip it. Okay, but your calculator is capable of doing that. If you actually punch in 0.01 and you hit the log button, it'll give you -2. And on your calculator, if you have one handy, if you find the log button, right above it will say 10 to the x. This is a calculator that's weird, but all regular calculators have log and 10 to the x on top of it. So because log base 10 and 10 to the x are inverse of each other, so they're basically on the same button. But now I can ask you this question. What is log of 17? I'm picking on 17 today. See, that I cannot do in my head. I know that log base 10 of 17 is something between 1 and 2. Maybe closer to 1. But my calculator will be able to do that. So if I punch 17 into the calculator and hit the log button, so 1.23-ish. Okay? So this means if I take 10 and raise it to the power 1.23, I'll get something really close to 17. Okay? And if I do that again, if I say 10 to the power 1.23, so 16.98, and that's the rounding error there. So this is your common log or log base 10. So we don't write base 10. Is that okay? Another logarithm that belongs to your calculator is a natural log. So this is log base e, that fancy number we learned last week. So natural log of x is really log base e of x. And we never write log base e of x, we just write ln of x. And every time you see ln, that implies log base e. Okay? So if I ask you what is ln of e, you will say, what? 1. If I say what is ln of e to the x, then you'll say x. Okay? So if I say what is ln of e to the pi, you'll say pi. Right? Is that okay? At the same time, if I ask you what is natural log of 10, that I cannot do in my head. No, no, this is just me writing. There's no reason for that line. So ln of 10, don't really know. But I have a calculator, 10, hit the ln button, so 2.3. Okay? So your calculator has these two buttons, log base 10 and log base e. So I can do any natural log. I can do any log base 10 on my calculator. Okay? But of course, if I go back to what were we trying to do, log base 3 of 8, kind of out of luck there. Okay? So, but how are you doing so far? Do you understand what the log does? Yes? So the output of a logarithmic function is really an exponent. It tells me the power, okay? The power to which I need to raise the base to get whatever the input was, okay? All right. So for any log base 10 or any log base e, we can do it on a calculator. For anything else, we can use what we call a change of base formula. And now I'm just going to give you the formula now. I won't be able to prove it. I need a few more tools, but I'll just give you the formula. Log base a of x equals log base b of x over log base b of a, where b is any base of your choice. So that means you can take any logarithmic expression and change it to any base that you like. All right? That b number is solely up to you. So if you were to change a logarithm to a different base for the purposes of computing it on your calculator, 10 or e, right? Your options are really limited there, right? If you want to change, so for example, if I want to do log base 3 of 8, I can change it to, let's say, base 10. So that will be log of 8 divided by log of 3. Okay? So if I do that on a calculator, log of 8 divided by log of 3, so 1.89. So that means if I raise 3 to the power 1.89, I'll get something really, really close to 8. If I do 3 to the power 1.89, I'm getting, 7.97, blah, blah, because of the rounding error. How's that? Sure. Here we go. Log base 3 of 9. We know the answer, right? 2. But I can still do that. I can still do change of base. That would be log of 9 over log of 3. So if I plug in log of 9, I'll get an ugly number. But if I divide that number by log of 3, the answer will come out to be 2. Because, well, as expected, we knew the answer is going to be 2. Is that what you were asking? Okay. Now, it doesn't have to be base 10. If I do log base 3 of 8, and I'll rewrite it as natural log of 8 over natural log of 3, I will still get 1.89 answer. So it doesn't matter to which base you change your logarithm. So 8 natural log divided by 3 natural log, I'm still getting 1.892. It's an identical result. So the change of base formula is, it's up to you to what base you want to change. But you shouldn't change log base 3 of 8 into base 7. That'll be redundant. because, well, you're stuck with a base that you still don't know how to compute. So we're still getting the same result. How's that? Oh yeah, this is we actually this is probably the chapter that's extremely applied. Well, I gave you here's an example. Don't write anything down, but let's just no, it's all right. Let's just talk about it. I gave you that PERT formula on Wednesday, the continuous interest, right? So and I'm jumping a little bit ahead because we haven't done any equations yet, but I can start solving equations. So for example, so let's do something realistic. Well, maybe not, but let's say you want to save up some money for something. Is that something you want to save some money for? What? A car. So you just want to walk in, put a pile of cash on the desk and drive out. That would be ideal. So how much is that car? All right, so we want to save $36,000. And let's say you're really bad at saving, you don't have enough discipline to put something each month into your savings account. But let's say you do have something in your pocket, or you just won a little lottery. A little lottery. Well, now you didn't win all 36K. You won part of it. How much would you like that to be? 1,700? All right. So let's say right now you have $1,700 to invest. Okay? So you're shopping around, you're looking for an investment opportunity. Well, the market tells you, well, give me that 1,700 bucks. I'll pay you 4.25% annual rate, which is pretty good by today's standards. So the rate is 4.25%, right? Well, how long will it take for that money to grow to that money? So here's the scenario, right? It's 36,000 equals 1,700 e to the power rate 0.0425 times the time, right? So you see the problem with that is that the unknown is in the exponent. See that? We haven't dealt with equations that have a variable as an exponent. But I can still solve this now. Because look, well, first thing what I'm going to do, I'm going to divide both sides by that 1,700. I want to isolate my e is just a number. Okay, it's that exponential. No, I cannot. E is the base here, so even if I divide by e, nothing good will happen. So 1,700 cancels, couple zero cancel on this end. So here I have e to the power 0.0425t equal 360 over 17. Right? Well, now, since we're already done a little bit of work, what if I ask you to rewrite this expression in the exponential, in the logarithmic form? Right, ln of 360 over 17 equals 0.0425 times t. So all of a sudden now, that's a linear equation. Because ln of 360 over 17, that's a number. I can plug it in my calculator. And to solve for t, I'll just divide by that constant in front, right? Another way to see how we got from here to here, remember when we just did, when we just solved, when we just studied the inverse, I kind of showed that we can use inverses to solve equations. So on the left side, I see an exponential function with a base e. So the inverse of that exponential function is a logarithmic function with base e. So it's natural log. So I can actually do this. I can take natural log of both sides, right? Now look at this. The left-hand side is our property 3. I have natural log of e to some power. Well, because of the e. That's what kind of tells me to use the natural log, but right now I'm getting this property working for me. I have a natural log of e to some power. Will give me some power back.
But if you ever put natural log in, it has to be on both sides.
Yeah. Right, it's on both sides. Did you plug in a calculator already? Oh, I don't know. So t equals whatever natural log of 360 over 17 divided by 0.0425. So yeah, I don't know. I trust your calculator, but if I do this, 360 over 17 is that many. Take natural log of that. Yeah, some humongous number. 0.0425. So down. 72 years almost. You'll have to wait for that amount to grow to $36,000. Yeah, the car might be gone by that, so you might want to do something else. You know. But this is just, 1,700 just sitting there, and you don't mess with it. You just let the interest to acquire. Okay, you don't put anything else in. But there are more complicated formulas, like, how much do I have to put each month? Let's say if I do the same amount of money month after month into that savings, so how long will it take for it to grow to $36,000? Considering the interest, we're not ready for those formulas yet, but it's still going to revolve around that. No. Well, again, as I think I might have. No, that's why the bubble bursts, because of that. No. People who invest money, they don't necessarily suck at that, but.
You don't use participation to invest money. You figure out your return on investment easier than figuring out how much you need to get to a certain point.
Yeah, I mean, this is just a very simplistic example, because again, I put a lot of conditions on that as far as. Yeah, there are financial calculators. You'll just hit the button and it'll tell you. No, people on Wall Street, I'm pretty sure, yeah, but if you go to a bank, there you might talk to people who have no idea. That happened to me before. I was talking to a lady, and I said something, and her job was she was one of the mortgage kind of a upper management personnel, and then I said something as far as, well, but then my payment would be blah, and she's like, well, how do you know that? I was like, well, clearly, blah, blah, blah. And then I say, and then you raise it to a power. And she went, well, what do you mean by power? And I got up and left. That was it. And good thing I did. But anyways.
I would have sat there and just rambled on about something completely wrong.
So, anyways. But there'll be, and then we'll deal with applications of that a little more. But yeah, I mean, this actually is applicable. And as I talked about on Wednesday, we'll be able to do a lot of models, not necessarily with money. We can do models with population. We can do that carbon dating. We can find bones and roots and see how old they are. I don't know if we'll actually do that, but we'll be able to do it theoretically. So how's this? Is that okay? All right, well, just a little more on graphs. Because again, all of the transformations and translations, they still apply. So if you're asked to graph something like log base 3 of x minus 1 plus 2. Okay? We understand what the graph of log base 3 of x is. It's just the graph of logarithmic function. Not really, just like with the exponential function, it's just steeper, right? The base 3 and base 2, base 3 is a little steeper, so with the logarithmic function, base 3 is a little flatter than, let's say, base 2 would be. But they're all going to have a generally the same shape. So let's talk about this. If I do -1 on the inside, where's the function going to shift? 1 unit to the right. So the intercept will shift 1 unit to the right. So will the asymptote. So now you have an asymptote at 1. So your graph does, yeah, it goes through the 2. But then what is plus 2 going to do? Yeah, so it's going to raise it up 2 units. So the graph will do something like that. Yeah, the vertical line will stay at 1. Well, if you do, well, the shifts over here will affect the vertical asymptote, right? So we shifted to the right, so the vertical asymptote went with it. But if you move up and down, that doesn't affect the asymptote anymore. But now we can actually find that x-intercept. We can actually find it. Because how do we find x-intercepts in general for any function? Set what to 0? Right, so say y equal to 0. So to find x-intercept, set y equal to 0. So we have log base 3 of x minus 1 plus 2 equals 0. So again, I'm jumping a little bit ahead. I'm about to solve a logarithmic equation because the variable is all the way on the inside of the log. So how do we solve any equation? So let's subtract 2 from both sides. So we get log base 3 of x minus 1 equals -2. Is that okay? You know, the first operation. And now what I'm going to do, I will rewrite in exponential form. And that means 3 is the base raised to that power, that's in the power, equals whatever's on the inside. So the same expression in the exponential form is 3 to the power -2 equals x minus 1. So 3 is the base, the output is the exponent, the input is the, the answer, whatever. So again, our equation turned into linear, and we can easily solve for x. Right, 1 and 1/9. Right? If I add 1 to both sides, I'll get x equals 1 plus 1/9, or 1 and 1/9. So just slightly greater than 1, as basically expected. So it'll be the x-intercept. Well, it did hit it at 2. If I just go over by 1, it hit it at 2. But then I shifted everything up. That's what changed that. And you see, and it just visually, if you take this dotted line over here and you start moving it upwards, your intercept jumped over there.
So how do you move it up? Do you just move like the bump higher?
No, you move the entire graph up, the whole graph. So like every change here was up 2 units, right? It went up 2 plus 2. Is that okay? Yeah, the vertical asymptote is still at 1, so you're still not going to touch that line. Well, whatever the shift occurs, so that's the horizontal shift that will drag your asymptote with it. So since we knew the original asymptote was at 0, and we have to shift the graph 1 to the right, so the asymptote will go with it, 1 to the right. The asymptote started at 0, but the intercept was at 1. Right. The original intercept was at 1 here. Yeah. Okay? But the big thing that you need to get from this section, the section 5.3, is the actual definition of the log, what it means, this little identity that allows you to jump between exponential and logarithmic form, because you saw that when I tried to solve equations, all I really had to do is to express one logarithmic and exponential, logarithmic is. And then I'm turning my exponential equations into linear, which like linear. So that's the big thing here. You know, understand how log works. Now these properties, these 4 properties again are important. And these 4 properties just for any general base, right? So as I tried a little bit later, I can rewrite those same properties for common log. Log of 10 equals 1. Log of 1 equals 0. Log of 10 to the x equals x, because I'm just using base 10 here. And 10 to the power log of x equals x, right? At the same time, I can write the same properties using natural log. So it's ln of e equals 1, ln of 1 equals 0, ln of e to the x equals x, and e to the ln of x equals x.
Is there just one homework again this week?
Yeah. So there's one assignment on sections 5.3 and 5.4 and one quiz. Okay? So this is, and I think your book introduces these properties in section 5.4. So these 2 sections are really, you know, connected. They just both talk about logarithms. So I'm kind of jumping all over the place. So okay, so these are the 4 properties. Now the laws of logarithms, again, if we understand that logarithmic functions give us exponents, because that's what logs are. Logs are exponents. They tell us what the exponent is. And if we understand the rules of exponent from, you know, earlier classes, there's a connection in between them. They kind of work. They kind of work the same way. So recall, no, it's e to the power ln of x. ln already has a base, and that base is e. So for the exponents, we have the product rule that says a to the power n times a to the power m is a to the power n plus m, right? So that tells you when you multiply expressions with the same base, you will add exponents. So that's the product rule. We have the quotient rule. That says if you take a to the power n and you divide it by a to the power m, that is a to the power n over m. Not that, sorry, you subtract exponents. Getting ahead of myself. And minus m. And then the power rule, if you take a to the power n and you raise it to the power m, that just a to the power n times m. Okay. Well, the logarithms have very similar properties. So we have a product rule. Product rule for logs, which is if you have a log base A of a product, am I remembering my properties correctly? Yeah. This is the same a log base A of A plus log base A of B. So the product turns into sum. We add exponents when we multiply expressions with the same base. So there, I hope you see the similarities between these two rules. When you multiply, you add exponents. Now, we can prove this. Don't write this down, how we prove this, but I'll just wait till you write that law down, and I'll show you how to prove it. So, the way we can prove this thing, I'm going to take a number A, and I'm going to raise A to the left side of this identity, which is log base A of AB. And I'm going to take A and raise it to the right side of this identity, log base A of A plus log base A of B. Don't write this down. It's just a quick proof. Now, I don't know whether that's equal yet. That's what I'm trying to show. Now, on the left side, by the property number 4 of our logarithms, when you have A raised to the power of log of the same base, then what does the left-hand side will be? Just AB, right? Whatever the input is. While on the right, I have A to the power that has an addition in it. And we just know you add exponents when you multiply. So the right-hand side can be rewritten as A to the power log base A of A times A to the power log base A of B. Just based on your rules of exponents. Is that okay? Well, now, what is log base A? I'm sorry, what is A to the power log base A of big A? Big A, right? And A raised to the power log base A of B, B. So AB equals AB, right? So it's kind of way to see that, okay? So the same thing works with the division. We have the quotient rule. And the quotient rule is dealing with the case when you have a log base A of A over B that becomes log base A of A minus log base A of B. And again, I can prove it in the same way. I don't want to. It's just the same thing. Yeah, on the right side you have a minus. Oh, Jesus Christ, man. So the power rule. And the power rule is dealing with this case when you have log base a of a to the power r. So I want to make sure we realize that what is raised to the power r is just this number a. Power r only applies, actually, let me rewrite this, not little a, that'll be boring. Just any expression like that. So we can, this is equivalent to saying r times log base a of big A. And again, it's very similar to our power rule for the exponents. When you raise power to a power, you multiply exponents. And again, I can prove this really quickly using that same trick I did on the first one. And again, you don't have to write this down, but if I raise a to the left side and I'll raise a to the right side, right, they are the same because the left side I have a is the base and the raised to the power log base a, so that just collapses to a to the power r, right? That's the left side. While the right side, I can rewrite the right side as a log base a of a raised to the power r like that, because that's when we multiply exponents, is when you raise power to a power. So the insides is just big A, and the little power stays on the outside, so it's the same. Okay? Now, why do you think the first rule is called the product rule? Because they're multiplied. Yeah, it has something to do with the product. And why do you think the second rule is called the quotient rule? Because there is some kind of division. But why do you think the third rule is called the power rule? Well, well, you can say that there's something that's dealing with powers. But I like to think the reason why number 3 is called the power rule because it's powerful. This is the most important rule of them all. Because what it just showed you, if you have a problem with an exponent, if your variable is an exponent, there is a way to drag that exponent down. So there is a way to turn exponential equations to linear equations, which is good news, right? Let me show you something. I'm jumping a little bit ahead of myself. But if I have this equation, don't write this down. 3 to the power x equals 7. By the way, I'm about to derive the change of base formula. Yeah. But let's say we don't know change base formula or anything like that, but let's say I'm looking at that equation, I see, well, the variable is an exponent, so is there a way to bring that exponent down? And then I look at my law number 3 at the power rule that shows me, well, if magically a logarithm appears in front of an exponential expression, then the exponent falls out, right? Now, this log is really, it's a free log. There's no conditions on the base A. So I can make that base anything I like. Since my calculator is very limited, I can flip a coin between base 10 or base E. Let's say it lands on base E. So I'm going to put natural log in front of this. I'm going to put natural log in front of the left-hand side. But then I'll have to do the same on the right-hand side, right? So basically, I end up taking natural log of both sides of this equation. Then by the power rule, that exponent just comes down. I can take this exponent, I can put it in front of the log, so this is x times natural log of 3 equals natural log of 7. Now it's a linear equation. I can solve for x. X equals ln of 7 over ln of 3. And I can plug it into my calculator. So 1.77-ish, right? Yeah, that's using the power rule. Now, if you notice, this expression in a logarithmic form would be log base 3 of 7 equals x, right? If I rewrite 3 to the power x equals 7 in a logarithmic form, it'll be log base 3 of 7. Well, and then change of base formula tells me that log base 3 of 7 is ln of 7 over ln of 3. So this is how you prove change of base formula. It's just solving an equation like that. So you can do it both ways. You can express it as a log and then use change of base formula, or you can bring the exponent down, like, you know, 2 approaches. Yeah, approximately or rounding. I don't know. No, on computer they'll tell you how many rounding. Yeah, they'll tell you, give me the answer to 3, 4 decimals. So you have to round. So yeah, just to prove change of base formula, again, you don't have to write this down, you just help me. So if I have log base a, let's say, of x equals y. Okay, so I want to derive change of base formula for that. So this is equivalent to saying a to the power y equals x, right? Then I want to bring the power down. We'll bring the power down by taking a log of both sides. And base could be anything, so I'm going to say take log base b of both sides. So I'll end up with log base b of a to the y equals log base b of x. Right? Just took log of both sides. Now by the power rule, the exponent comes down. So it becomes y times log base b of a equals log base b of x. And then solving for y, because that's what we're trying to solve for. I want to get y. Y equals log base b of x over log base b of a. So log base b of x, log base a of x equals that. So that's our change of base formula. Okay? And again, b is totally up to you, so you can make it log of x over log of a, ln of x over ln of a, it'll all equal the same thing. Okay? So you need to know that formula. You need to know the change of base formula, because I might just ask, just computing basic logarithms. But it's really easy to remember, and one trick that I always tell my students, the way just notation works for the logarithm, just the way it works, we write the base kind of below. So the base appears below the x, right? Just the way we write it. Well, that same thing with the formula. The base is below the x. So if you just remember that, it's going to be log of x over log of a, then you're good. So again, we already did those examples, but if I ask you what is log base 4 of 15 is, you'll just go, okay, how about natural log of 15 over natural log of 4? Okay, and I'll give you the answer by plugging it into your calculator. So very close to 2, as expected, right? 1.95-ish.
Why is the base of log? Like, what do you do base for the, like, why is it standard, I guess?
Well, it's just because we go all crazy for number 10 for whatever reason. 10 is just because we live in base 10. Well, on paper. But we see with out of all numbers other than 10, we just chose that really weird e to be another special log. So, no, e is a specific number. It's this. No, e is that. That's what e equals to. 2.718. Yeah, that's different. Yeah, I see what you're saying. Yeah. He's talking about when your calculator gives you that and then says like e with the power. Like that's the scientific notation. Yeah, that's different. Yeah. This is the base e that we talked about on Wednesday, the Euler number. Okay, I'm actually going to stop now. I'm not going to go on. I gave you enough to digest. Yeah, you can start your homework to an extent. I mean, I can keep going, but I'll just finish both sections. You should be able to do most of the homework now. Not all of it, but most of it. I got your email.